All right, everyone, and we are back, and I want to do a quick example for a cantilever beam for beam bending. So let's say I have a beam. It's of some, we have our coordinate system, x, y. This is x equals 0. We have x equals L here. I have, let's say, a 10 Newton load applied at the end of the beam, and I want to set this up for my beam bending. Now, the way I typically like to start is I know I can write out this equation, E dot I. I'll show you the dimension of the beams in just a bit, but y quadruple prime of x. Set that equal to q of x. In this instance, because it's a point load, our q of x is going to be equal to minus 10 times Dirac delta times x minus L. And we're going to set up our boundary conditions where we know the deflection of our beam at 0. So y of 0 is equal to 0. Y prime of 0 is equal to 0. We know that there should be no restoring moment or bending moment to the beam here at the end. So we know that E dot I dot Y double prime at L is equal to 0. But we need to find our last boundary condition. And I'm going to solve, we can solve it either for the shear moment or for the bending moment. So I want to do it for the bending moment. E dot I dot Y double prime of 0. And that's going to equal some value. So what we're going to have to do, and we need to look at, in that beam initially, we have a force here of 10 newtons. We also have some restoring force here. I'm going to call it F of y. And as this turns, there's going to be some opposing moment from that fixed boundary condition there. There's also force in the x direction, but that's going to be 0 in this instance. So, yeah. So actually, wait, it's going to go here. Yeah, that's going to be the restoring moment direction. But we'll find it out mathematically. So let's solve for f of y and f and our moment. So I'm going to say, and I'm going to calculate the moment from this position here. So I'm going to say that the sum of the forces in the y direction must be equal to 0, and that's going to be equal to f of y minus 10 newtons, because pointing down. So our f of y is equal to 10 newtons. Some of the moments at that point that we indicated. So we have, basically, there's a positive m here, and then that moment from this force is going to be the minus 10, because again, we're doing counterclockwise, minus 10 times L, so our moment's going to be equal to 10L in that direction. So when I'm trying to find my bending moment at that origin, I need to draw my bending moment diagram. But really all I have to do is look at this. So I make my cut here. This is my V. There's going to be some mx. We have this moment here, m. We have our f of y here. And you have the minus v. There we go. So let's calculate what the moment's going to be. And I'm going to do the moment. There's some distance here, x. I'm going to do the moment from right here. So I am going to say there's no moment from this v, so my sum of the moments at that origin must be equal to 0, so it's going to be equal to plus mx plus m, because they're still going counterclockwise, minus f of y times x, right? That distance, because we have to change and flip our direction. So we're left with an expression that my bending moment mx is going to be equal to minus m plus fy dot x. So what's the moment at 0? Well, this reduces, so now I'm just left with minus m, and we've already defined that m is equal to 10L, so we can solve it there. But what about our shear moment? Well, I can do some of the forces in the y must be equal to 0, and that's going to be equal to f of y minus v. So then my shear moment, then v is going to be equal to 10 newtons, or f of y, right? Because f of y is equal to 10 newtons here. So I can now plug in both of those conditions. So I'm doing a polymer beam. It has this dimension here, this dimension here. I can shift enter, minus 10 Dirac delta. I have my initial conditions, and see, I've solved it here both ways, for the moment and for the shear moment diagram. So I can set those initial conditions. I'm going to copy and paste in the solution here. And we can look and see what does the deflection look like. Hopefully it will be just basically pointing down. And it is indeed, once I shift enter. We can find the minimum, or basically the displacement of the beam. We can see that happens at the end. We could also find, now that we have our deflection equation, we can find the moment. And we see, as you'd expect from a cantilever beam, we are in negative curvature. So our moment is at that origin is negative. And the top of the beam should be in tension. So we'll pull out and find the minimum moment, which is just that, basically the dimension here, L. Let's just pull that out. L is equal to 1/10. So we see that we're in negative curvature, so I'm just going to paste this minus the moment times the top of the beam, because I'm just looking for maximum stress. And we see that the stress is going to be positive. Makes sense. If we were looking at the bottom of the beam, so minus h/2, then we'd have compression. Makes sense. And then we can look at a shear moment diagram, which should be just a constant 10 newtons and positive. And there we go. So, and we can find like the shear value at any point. We can find the bending moment value at any point by just kind of plugging in. So I want to say, like, I want to find the moment where x is 0.075, and then I can find that value there. Yeah, that's pretty much it. So this is how you set up and get your bending moment diagrams, and how you deal with beam bending and connect it to kind of statics. So we'll see you in the next video. Thanks.